Another thing we can do is break down the Stefan-Boltzmann law by wavelength. So what we can do is go back to the integral itself that was involved right before we derived the final step to the Stefan-Boltzmann law. So what I'll do is I'm going to take that integral that appeared there, which was something like is an integral over what we had called x to the third over what is essentially the Bose-Einstein distribution. And what I'll do is I'll make a change of area. I want to change from x and I'll change that back to wavelength. So first I'll try and highlight what the wavelength is, and then I'll just redefine the differential. That'll bring out a factor of minus d lambda over lambda squared when I go to calculate the differential, and then that'll help me pull out some extra prefactors. But the important thing is that the integral that's there now has something that looks like 1 over lambda to the 5th power, and then times something that again looks like the Bose-Einstein distribution as the integrand. Then what I'll do is identify the integrand, and I'll call that, essentially that plus some prefactor would be the heat flux, right? So what I'll do is I'll think about that as a heat flux integrand. So that's sort of like the heat flux per unit wavelength. And that would be some constant based on a bunch of universal constants times 1 over lambda to the 5th times essentially the Bose-Einstein distribution. And of course, if I integrate that wavelength-dependent heat flux over all wavelength, I would get back the total heat flux going through my surface element. And we can identify what those constants are. And they're of course all based on the speed of light, Planck's constant, and the Boltzmann constant. All known constants of the universe. Then what's interesting is to go ahead and plot what that wavelength-dependent heat flux looks like, or what is the breakdown of which wavelengths are carrying most of the heat in some sense. And what you find is that those two functions that appear in the integrand actually have opposite shapes and sort of trace out something that has a maximum somewhere in between. You can ask yourself, where is that maximum? And of course, the mathematical way to answer that is to take the derivative with respect to wavelength and then look at where that's equal to 0 to find the maximum. And if you do that, what you find is that basically there's some value of the exponential that makes that always true, and that basically ends up helping you find what is commonly called Wien's displacement law, where you find out that the position of that maximum times temperature is equal to a universal constant. And in fact, you can work out what that constant is. It turns out to be 2.89 e to the 6 nanometer Kelvin. And then you have to divide by the temperature in order to figure out what that maximum wavelength is. Now, at room temperature, that wavelength turns out to be something like 10,000 nanometers, which is pretty long wavelength. You can't see that with your eye, which is why, of course, infrared cameras have been developed to help us see farther in that region. At the temperature that the sun's surface would be at, it's more like hundreds of nanometers, and therefore in the visible wavelength range. So depending on which surface temperature of the sun you claim is true, it'll either be somewhere around the yellow or orange range.